So it's a means. I took that window, and in my head, I was fishing for applications. Well, applications then could be architectural, but whatever you pull out of that lattice is going to be in proportion. And you can take it further. So this is the first part. How am I doing time-wise? This is the first part, the first idea I wanted to show you that I extracted from the past. I want to show you another one. Hopefully you'll find this more fun in a way. The other one's kind of abstract, but it shows a process. So this one, where do I fish for my ideas? Well, I was aware of the Greek solids. They call them Platonic solids, Archimedean solids. Are you guys aware of those? I mean, cube is one of them. But there's a bunch of others, tetrahedron, octahedron, there's a bunch of them. This is the range. And you often see them in a math lab at school, hanging, made of straw or something, and just hanging there. Does anyone ever tell you that they combine? Who knew that those geometric shapes can combine? Give me an indication. Who doesn't know that? Oh, there's hope. This is good. So, sorry, I didn't mean to be condescending, but it's cool. So they do combine. And drifting back to the spheres, you can construct these with spheres, which means rather than just abstract from the sphere world, these guys, you can also extract their internal lattices. It gives you so many more structural possibilities. So you just are not trapped by these, polyhedra. So, Rome, I travel, I look, think. Two shapes particularly, square and the diamond. That's a 45-degree rhombus, but it's a diamond. And here, there's something called a makana. It's an Islamic structure that transitions space. So if you go from a flat surface to an arch, it's often used like a stalactite to transition the space. So they combine these polygons, or originally polygons, in a fixed way. And here's a Victorian toy. So this is all the junk that ends up in my mind. I mean, it's pretty worrying, but still. So I started to think, well, you have fixed relationships between these shapes. You have movable relationships. Why not connect them flexibly? So these are the same two shapes, flexibly connected. And what's kind of interesting is that they're modular. So that means if you made 1,000 of these things, they'd all fit and interconnect. You start to fill space here with a flexible, shape-changing kind of world. Are you familiar with shape changes? Because that's where I'm going with this. So I started analyzing these. And that's the same module as the one you just saw. But it shows its equilibrium positions. This guy, each of those is a stable position. In between, the shape is transforming, but then it finds a balance, a point of balance. And of course, then you can kind of interconnect them. This is the same module. And again, same module. So what you're doing here, I mean, if you were using these in packaging and architectural, you're really creating structures that can transform from filling space to being compact. You've seen that with cardboard boxes. You can fold them flat, you can fold them up. Well, here's a way of being kind of a bit more creative. They stack. Same module. It stacks. Here's another one. Same shapes, but arranged differently. So it only has 3 different positions. And again, you can combine, and you can make them fill space. And they stack. It's very simple. It's just two shapes, a square and a diamond, 45-degree diamond. If you triangulate them, if you bring those forms to touch each other and they triangulate, they become fixed. Triangles are stable, they're fixed. So you can have the shape-changing characteristic or the fixed characteristic. Here's another one. This is 60-degree rhombus. So it's diamond, 60 degrees. Goes flat. And again, this is that one, the third one, and it transforms, fills space. Here's another, and I'll kind of zip through these. Here's another. Flat, they go three-dimensional. These can be macro-sized, micro-sized. They could be tiny. It could be a wall with some of these on, with tiny versions of it. You mass produce that. You could use what are the sort of silicates that change shape and really program the changes. Here's another one. Flat comes out. It's very simple. Here's another one. This is squares and triangles. And another. This one's just squares, flexibly connected. So you can create all sorts of forms that will transform from one to another. This is how they stack, some of them. Now, if you are interested, I can leave my email and I can send you templates of some of these guys. I mean, maybe you can do it through the school or whatever, but we'll work that out. But I can send you templates, as much as I can send you three-dimensional models of those spherical structures, which you can mess around with. So I can make those 3D models available, or I can make templates of the shape changes available. Anyone seen this guy before? So they're called thermoformers. You apply a charge to the thermoformer and it changes shape. Means you can program it. And at MIT, they're actually making this as in layers, like a single. You take a whole sheet, die cut it, you go in with your thermoformers, you go in with your conductive circuit, you got a microchip, you program it, it tells the formers when to change shape. This, not formers, this is the Duddeney transformation. I didn't invent this, a guy called Duddeney did. But it shows how, if you start to bring that into your mindset, how you can start to develop it. Now, if you were interested in shape changes, the onus is on you. You do the research, you think about it, you see what you come up with. But start to think, surfaces do not have to be stable. Forms can change shape. It's your option. NASA. It's got a sort of silicate skin. Within the silicate skin, you've got a whole bunch of different shape changes. And they are transforming that wing form. So the wing is being swept, it's flaring, it's even splitting. Huge. You can now start to have a form that moves in three-dimensional space that can adjust its form to accommodate its speed, air pressure, heat, could be architectural. It might sound fantastic. It's just a possibility. Something that could be explored, maybe in a simple way. It might just be a mirror on a car, or it might be the whole car. I mean, it's how you think about it. And I love this one, and this is the last one. Festo, it's a German company. It's internal. Anyone seen this before? No? Mylar structure. various types of shape-changing linkage inside. Thing flies. Of course, I wouldn't like to put it out in the air because it'll be blown away. It's very light. So what they did is they went under the water. They started creating these guys. And if you go online, you'll find it. Festo, F-E-S-T-O. And you'll find undersea structures. And that makes kind of more sense for the logic. So you've got shape changes. And you've got ways of filling space. That's the spheres. And I'm kind of summarizing here. But I just wanted to share that with you. It's just like how I work, how I analyze, how I research, how I think, put stuff together. And of course, there's a lot of hard work behind all of this. But I just wanted to share that with you. And that's really the end of my presentation. Thank you.